All right. So we'll throw some light on geometrical optics today, and few basic things before I dig into the core geometrical optics. Some basic understanding of jargon associated with geometrical optics. Let me get you introduced to those things first. So first of all, I want to define an optical property of a medium. Optical property of a medium. In context of optics, a medium is characterized by a property called the refractive index of the medium. Mu m, which is the refractive index of a medium m, mu m, which is the refractive index of a medium m, now that's defined as the velocity of light in vacuum. Vacuum and air would be regarded almost synonymous in terms of their optical properties. Velocity of light in vacuum divided by vacuum or air, which is considered the same, divided by velocity of light in the medium m. Velocity of light in the medium m. So if c is the velocity of light in vacuum, which you know is 3 into 10 to the power 8 meters per second, c is the velocity of light in vacuum, divided by Vm, where Vm is the velocity of light in the medium m. This is referred to as the refractive index of the medium m, and by and large, all optical behavior of a given medium would revolve around this property, the refractive index of the medium. Alright. Now, based on this property, a few more ideas. One, an optical path length. Optical path length, sometimes just referred to as optical path. When I say optical path, I would mean optical path length. Suppose a ray of light travels from A to B. Suppose a ray of light travels from A to B in a medium of refractive index mu m. A medium of refractive index mu m. Then the actual length that it covers in that medium, AB, is the geometrical path that the ray covers. This is the geometrical path. The length AB is the geometrical path covered by the ray in that medium. The optical path or the optical path length is the equivalent path in air. I'll define that. Is the equivalent path in air. In air or vacuum. Now, what is it that I mean by an equivalent path in air or vacuum? Look, to go from A to B in a medium of refractive index mu m, in order to go from A to B in a medium of refractive index mu m, the time taken by the ray of light would be distance by velocity in that medium, which would be AB. divided by the velocity of light in the medium m. Divided by the velocity of light in the medium m. That's the time taken to traverse the geometrical length AB plus u. In the same time, the distance travelled by a ray of light in vacuum, in the same time t, the distance travelled by a ray of light in vacuum is said to be the equivalent optical path or the optical path travelled. That means in time t, it goes from A prime to B prime, where A prime, B prime is the equivalent path in air. A prime, B prime is the equivalent path in air. Travels a distance A prime, B prime in time t, which would be velocity of light in vacuum into time t. Velocity of light in vacuum into time t, that would be A prime, B prime. So, C into time t, that's the equivalent path in air or the optical path length or the optical path length. That means this is C into T. T is like a AB by VM, where VM is the geometrical path. AB is the geometrical path. So AB by VM, where C by VM is mu m into AB. That's the equivalent path traversed in air, referred to as the optical path length. So if AB is the geometrical length covered by a ray of light, if AB is the geometrical path covered by a ray of light in a medium of refractive index mu m, then the optical path corresponding to AB would be mu m times AB. That means the refractive index of this medium into the geometrical path would be the optical path or the equivalent path in air, right? So, by default, if we talk of the path of a ray in a given medium, we are actually referring to the optical path. By default, we are referring to the optical path. In air, if a ray of light travels in air, then optical path will be equal to the geometrical path. Because refractive index of air would be velocity of light in air divided by velocity of light in air, right? So that would be 1. Refractive index for air, refractive index mu is 1. And therefore the optical path and the geometrical path coincide for air. If mu is not 1, that means for some other medium which is not air, optical path will be mu times the geometrical path, right? Optical path would be mu times the geometrical path. So each time you have a given geometrical path multiplied by the refractive index of the medium, you will get the optical path in that medium, alright, which is the equivalent path in air, alright. Again, sometimes we end up comparing two media optically. We compare two media optically. Say this is medium M1 and this is medium M2. This has refractive index mu1 and this has refractive index mu2. If mu1 is greater than mu2, if the refractive index of M1 is greater than the refractive index of M2, then we say that M1 is optically denser than M2. M1 is optically denser than M2. M1 is optically denser than M2. Or we say M2 is optically rarer compared to M1. So whenever we talk of optical density, we are actually talking of the refractive index of the medium. Refractive index of the medium. If one medium has a high refractive index, we say it's optically denser. If a medium has a low refractive index, we say it's optically rarer. Right? Are you okay with this? Now, something more fundamental compared to laws of reflection and laws of refraction, something that forms the basis of the laws of reflection and laws of refraction are common base for both these prominent principles in geometrical optics is the following. If a ray of light has to travel from a point A to a point B, write down. If a ray of light has to travel from a point A to a point B, by means of getting reflected or refracted, by means of getting reflected or refracted, it will choose an optical path. It will choose an optical path. It will choose an optical path that is either a maximum, or a minimum. An optical path that is a maximum or a minimum, write down, an optical path that is a maximum or a minimum, an optical path that's a maximum or a minimum is referred to as a stationary optical path, Laws of reflection or refraction. Laws of reflection or refraction originate out of this principle. Now, let me illustrate, let me explain. Suppose there is a point A and another fixed point B, right? And say there is a reflector. Let's say a plane mirror. With respect to the plane mirror, the points A and B are fixed. Let me locate points A and B by two numbers, H1 and H2. Now we want a ray of light to go from A and B after having suffered reflection at the mirror, Now, there are so many ways the light could travel from A to B having suffered reflection at the mirror. For example, it could go like this and then head towards B, or it could go like this and then head towards B, or it could go like this and then head towards B, and so on and so forth, right? There are very ways the ray of light could go from A to. Now these various paths, right? This was one optical path which would be mu times the corresponding geometrical path. This was another optical path which is mu times the corresponding geometrical path. Yet another optical path, so many optical paths permissible between A and B. The one that light is going to choose in its traversal from A to B is the one which would either be a maximum or a minimum. Although we learn that in a plane mirror it will choose the minimum path, but in any case, the optical path that is chosen for its traversal from A to B, having suffered reflection at the mirror, would be a stationary optical path. Now, realize that eventually The horizontal separation between A and B is a fixed number C. The horizontal separation between A and B is a fixed number C. Got me? Now, it could choose any one of these paths. For example, this is PQ. And let's say it chooses this path, ARB. Suppose it chooses this path, ARB. Right? So, if I select PR to be X, then what's RQ going to be? C minus X. RQ then is going to be C minus X. So then, the length AR would depend on X. The length AR would be root H1 squared plus X squared. The optical path, suppose mu is the refractive index of this medium. Then what is the optical path? Optical path OP is mu times AR plus RB. Mu times AR plus RB, that's going to be the optical path, right? Where AR and RB are the geometrical paths. So AR will depend on X, root H1 squared plus X squared. RB would depend on X, because RB would be root C minus X whole squared plus H2 squared, and so on and so forth, right? So then, this would be a function of X. The optical path will depend on X. For different values of X, you're going to arrive at different optical paths. Now, for again, something that I'm resounding right now, but a detailed discussion of this statement would be pending in calculus. But for the time being, let me tell you that if this is a function of X, and when I say that this is stationary, that is either a maximum or a minimum, then the derivative of this with respect to X must be 0. If there is a function of X, and that's either a maximum or a minimum, then its derivative with respect to X must be 0. That means, for this to be stationary, we must have f dash x equal to 0. That means ddx of this must be 0. ddx of mu times AR plus RB must be 0. Such should be X. Alright. So now, let's formulate the principle. Can I wipe this off and just find out the value of X for which this is going to be stationary? Can I wipe this off? A plane mirror. There is a fixed point A, located by a number H1, another fixed point B. To locate B, a number H2. The horizontal separation between A and B, PQ, is C. Horizontal separation between P and Q, call it C. Suppose, to go from A to B, the ray of light has to pay tribute to a certain point R, and then heads towards B. This then is said to be the normal at the point of incidence. And this angle I is said to be the angle of incidence. This angle R is said to be the angle of reflection. And then from geometry you can say that alternate angles, this is I, alternate angle. This is R, right? And we need to locate R. P and Q are fixed, we need to locate R. To locate R, call PR as X. So RQ would become C minus X. RQ would become C minus X. So then the optical path is going to be mu times AR. Mu times AR. But what's AR? Root H1 squared plus X squared plus RB. RB is root H2 squared plus C minus X whole squared. H2 squared plus C minus X whole squared, right? That's the optical path, which is a function of X. How would X be determined? From the fact that ddx of this must be 0. For this path to be stationary, the derivative of this with respect to X must be 0. Such should be X. Such should be X. Right? Now, even before I proceed, let me quickly tell you, ddx of root H squared plus H1 squared plus X squared. What is it going to be? To the power half. That's going to be half of H1 squared plus X squared to power minus half, right? Outside to inside, half into this to power half minus 1 into 2x, which is x by root H1 squared plus X squared. ddx of this would be x by root H1 squared plus X squared. Clear? Similarly, can I wipe this off? I hope you haven't forgotten chain rule by now. Similarly, ddx of H2 squared plus C minus X whole squared to power half. Again, go from outside to inside. This is H2 squared plus C minus X whole squared to power half minus 1, that is minus half, into derivative of, then C minus X whole squared would give me 2 into C minus X, and then C minus X would give me minus 1, minus 1. Right? Which is like, and of course 1 by 2 of this, right? So that makes it like a C minus X minus of C minus X divided by root H2 squared plus C minus X whole squared. H2 squared plus C minus X whole squared, right? That's how you differentiate these. Okay. Now, so this is optical path, OP. What should we have? ddx of the optical path must be 0. ddx of the optical path must be 0. Such should be x. ddx of the optical path must be 0. Such should be x. Right? Which would give me, can I wipe this off? Which would give me, when I differentiate, it would give me x by root H1 squared plus X squared minus C minus X by H2 squared plus C minus X whole squared equal to 0. This is what I get when I differentiate with respect to x equated to 0. For the optical path to be stationary, the derivative of this with respect to x must be 0, right? Hey, but what is x by root H1 squared plus X squared? This is x divided by this. This is root H1 squared plus X squared, yes or no? This is root H1 squared plus X squared. So x divided by AR, that's sin I, that's sin I. So this is sin I, this is sin I minus C minus X divided by root H2 squared plus C minus X whole squared is sin R. That must be 0. Therefore sin I equal to sin R and therefore I equal to R. That's how you've known the laws of reflection. Angle of incidence equal to angle of reflection. The more fundamental law is the optical path must be stationary. The optical path must be stationary. The derivative of this with respect to x must be 0, causing I to be equal to R. Angle of incidence to be equal to angle of reflection. Got me? हाँ? म्यू तो बाहर नहीं आ जाएगा. म्यू टाइम्स ddx of this is 0. हाँ? Mu into sin I minus sin R is 0, but mu is not 0. Right? Mu is not 0. So sin I minus sin R must be 0. I mean, there was a mu here, but that's all right. Since mu is not 0, this must be 0. This is inside mu. Right? Now, let's look at what happens in refraction. Let's look at what happens in refraction. So when we talk of refraction, we talk of two distinct optical media. We talk of two distinct optical media means optical media with a pair of optical media with different refractive indices. So suppose this is a medium with a refractive index mu1 and this is a medium with refractive index mu2. And you want a ray of light to go from a fixed point A to a fixed point B. You want a ray of light to go from a fixed point A to a fixed point B. A and B are two fixed points. Alright. So you want to locate A and B like before with respect to this. This is the boundary separating the two optical media. This is a plane boundary separating the two optical media. So locate A by a number H1 and locate B by a number H2. Right. And in order to go from A to B, the ray of light has to select this point. This point would have to be selected. This is a variable point, right? It could be anywhere. Right? So this is PQ and R is the variable point. This point is the variable point. So let's say the horizontal separation between P and Q, like before, is C. PQ is C. And locate PR by a number X, which is a variable. For different values of X, you will have different R's, right? And then R becomes C minus X. R becomes C minus X. How about this? RQ becomes C minus X. RQ becomes C minus X. This is the normal at the point of incidence. This is the normal at the point of incidence. This is I, angle of incidence I. This is said to be the angle of refraction R. This is said to be the angle of refraction R. And then this is alternate angle I, and from this is alternate angle R. This is alternate angle R. Clear? Now, what's the optical path? The optical path here is mu1 times AR plus mu2 times RB. Mu1 times AR plus mu2 times RB. Right? Mu1 times AR. What's AR? AR is root H1 squared plus x squared mu 2 times RB. RB is what? Root h2 squared plus c minus x whole squared. RB is root h2 squared plus c minus x whole squared. We already know how to differentiate these two. So, the traversal would be such that ddx of the optical path must be 0. ddx of the optical path must be 0 for the path to be stationary. So, that's going to cause mu1 into x by root h1 squared plus x squared minus mu2 into c minus x by root h2 squared plus c minus x whole squared. This must be 0. Such should be x, right? But x by this, x divided by root h1 squared plus x squared is sin I, and like before, c minus x divided by root h2 squared plus c minus x whole squared is sin R. So we get like a mu1 sin I minus mu2 sin R is 0. Right? Which means mu1 sin I, mu of the incident medium, this is the incident medium, this is the refracting medium, mu1 into sine of the angle of incidence must be mu2 into sine of the angle of refraction. And that's called generalized Snell's law. That's called generalized Snell's law. Generalized Snell's law. And when there is just one medium, then we are talking of reflection. Then mu1 becomes equal to mu2 and I becomes equal to R. So, the laws of reflection really are a special case of laws of refraction. Right? Got me? Now wipe this off. Now, we then have sin I by sin R. Sine of the angle of incidence divided by sine of angle of refraction as mu2 by mu1. Refractive index of the refracting medium divided by refractive index of the incident medium. This mu2 by mu1 is said to be the refractive index of the second medium with respect to the first. This is said to be the refractive index. Absolute refractive index of the two media are mu1 and mu2, but mu2 by mu1 is the refractive index of the second medium or the refracting medium with respect to the first. Refractive index of the second medium with respect to the first. Mu2 by mu1 written as mu of 2 with respect to 1. Refractive index of the second medium with respect to the first medium. And this is a constant for a given pair of optical media and for a given color of light. If you change the color of light, then this sin I by sin R will have some other ratio. Same pair of media but a different color of light will give you a different value of sin I by sin R. So for a given color of light, and for a given pair of optical media, you have sin I by sin R equal to a constant which is refractive index of the second medium with respect to the first medium. And then another principle which is very relevant in geometrical optics is the principle of reversibility of light. See, if it had to go from A to B, it will take up this path. But if it had to go from B to A, it will take up this path. That's the principle of reversibility of light. To go from A to B, if it has assumed a certain path, then to go from B to A, it will assume a reverse path. It will assume a reverse path, and that's principle of reversibility of light. That's principle of reversibility of light. Got me? Now, suppose a ray of light goes from an optically denser to an optically rarer to an optically denser medium, for example. Optically rarer, optically denser. Which means if this is mu1 and this is mu2, then mu2 is greater than mu1. That's when mu2 is optically denser than mu1, right? This is I, this is R. So we have like a mu1 sin I equal to mu2 sin R. Mu1 sin I is mu2 sin R. Right? That's Snell's law applied at the point of incidence. Mu1 sin I is mu2 sin R. And if mu1 is less than mu2, if mu1 is less than mu2, then sin I would have to be greater than sin R for the product to be the same. So sin I would have to be greater than sin R. If mu1 is less than mu2, then this has to be greater than this for the product to be equal, right? So sin I would have to be greater than sin R, or I would have to be greater than R, right? If I is greater than R, that means the ray of light bends towards the normal. Ray of light bends towards the normal. So when it goes from an optically rarer to an optically denser medium, the ray of light bends towards the normal. And from the principle of reversibility of light, if it has to go from an optically denser to an optically rarer medium, it's going to bend away from the normal. That's out of principle of reversibility of light. Yes or no? So from an optically rarer to an optically denser medium, it will bend towards the normal. And from an optically denser to an optically rarer medium, it's going to bend away from the normal, right? Now, can I wrap this up? Both reflection and refraction have one thing in common. They deviate a ray. Both reflection and refraction deviate a ray from its normal course, right? From its original line of traversal, the ray gets deviated. The ray gets deviated. So it's important that we quantify the extent of deviation produced in a ray out of reflection and refraction. Alright. Say, this is a mirror. This is an incident ray. This is the normal at the point of incidence. This is the reflected ray. This is the reflected ray. Let's say this is the angle of incidence I. This would be angle of reflection, which is also I. We've already figured that out. Angle of incidence equal to angle of reflection. Now, the deviation produced upon this ray because of reflection. Now, what would have happened if no reflection had occurred on this surface? This original direction would have maintained status. It would have gone this way. This ray would have travelled this way. In the absence of the mirror, the ray would have travelled this way, right? It would have travelled rectilinearly along this line. Now, because of the mirror, because of reflection, it goes this way. It goes this way. We then say that the ray has got deviated by this amount. The ray has got deviated by this amount, yes or no? Instead of going this way, if it's going this way, that means the ray has got rotated by this amount. The ray has got rotated by this amount. Then this angle is said to be the angle of deviation or simply deviation. This angle is delta, the deviation produced. This is said to be delta, the deviation produced. Now, evidently then, this angle is 180 minus 2i. You realize that this angle delta in magnitude is 180 minus 2i. So, in reflection, the deviation produced by a single reflection is pi minus 2i, where I is the angle of incidence. Sometimes we don't talk of I. We talk of these angles. For example, suppose this angle is alpha, which is 90 minus I. This angle must also be alpha, which is 90 minus I. How about it? Right? Then, if this angle is alpha, realize that vertically opposite angle, this is also alpha. So, we then say that the deviation is 2 alpha. In terms of alpha, the deviation is 2 alpha. In terms of alpha, the deviation is 2 alpha, where alpha is said to be the grazing angle of incidence. I is the angle of incidence, where alpha is said to be the grazing angle of incidence. Alpha is said to be the grazing angle of incidence. So, if you have alpha, the grazing angle, then the deviation produced is going to be 2 alpha. Right? Now, in this case, there is a sense of deviation also produced, right? The ray would have gone this way, now it's going this way. So, is the deviation clockwise or anti-clockwise? In this case, the deviation is anti-clockwise. For the figure that I have drawn, the deviation is anti-clockwise. For this figure. A ray of light could suffer multiple reflections and refractions, combination of both, right? It would undergo deviation on one surface, it would undergo deviation on another surface. See, for example, this ray, this reflected ray could have hit another mirror here and would have gone this way and would have gone this way. Yes or no? And then realize that in the absence of this mirror, the ray would have travelled in this direction. But courtesy the mirror, it travels this way. So, what's the sense of deviation here? Clockwise. So, this was anti-clockwise deviation, this is clockwise deviation. Now, the total deviation because of these two is the algebraic sum of the deviation. Would be the total deviation when number of deviations take place because of multiple reflections and or refractions. And if it's algebraic deviation, when there is more than one deviation involved, you must assign suitable signs to deviation. The convention is, although you can depart from this convention, there will be no loss of generality in doing so, but the regular convention is all anti-clockwise deviations are regarded positive, all clockwise deviations are regarded negative, like we did in trigonometry, with the rotating line. All clockwise deviations were deemed negative, all anti-clockwise deviations were deemed positive. Got me? So, when you have multiple reflections or refractions, then the total deviation would be the algebraic sum of the deviations, all the deviations. Clear? So, that's the story of deviation in reflection. Let's look at the story of deviation in refraction. Alright. Could I wipe this off? Right. So, say if there is a ray of light which is going from an optically rarer medium to an optically denser medium, optically rarer to an optically denser, you know that it's going to bend towards the normal. From an optically rarer to an optically denser medium, a ray of light bends towards the normal. This angle is I, angle of incidence. This is R, angle of refraction. Now, if the refraction had not occurred, this is the incident ray, this is the refracted ray, right? If the deviation had not occurred, that means if the refraction had not occurred, then this ray would have propagated along a straight line like this. This ray would have gone along the dotted line in the absence of refraction, but now it goes along this line. That means, what has refraction done to the incident ray? It has rotated the incident ray by this amount. It has rotated the incident ray by this amount, so that instead of traveling along this, it travels along this. This then should be the deviation produced. Evidently then, if this is I, then this angle, vertically opposite angles, this is also I. So what's the deviation delta? I minus R in this case. In this case, the deviation is I minus R. And again, if there are multiple deviations in a system, then you will take the total deviation as algebraic sum of the deviation. But if there is just one single deviation, you can just call it positive. But in multiple deviations, all anti-clockwise deviations could be considered positive, and all clockwise deviations could be considered negative and looked upon as the algebraic sum, right? So in this case, the deviation is I minus R, right? If a ray of light traveled from an optically denser to an optically rarer medium, this is optically denser, and it traveled into an optically rarer medium. Suppose it traveled from an optically denser to an optically rarer medium, it bends away from the normal. This angle is I, angle of incidence. This angle is R, angle of refraction. If refraction had not occurred, this ray, incident ray, would have gone this way. But now it goes this way, right? So the deviation produced is this delta, which is going to be R minus I, because this vertically opposite angle is I. So in this case, delta is going to be R minus I. Deviation is going to be R minus I. Clear? Now, let me look at two plane mirrors inclined at a certain angle. Okay. Let's say they're inclined at a certain fixed angle, theta. Call this mirror 1, call this mirror 2. Let's say there is an incident ray, IR, incident at a grazing angle, I1. Incident, this is not angle of incidence, this is grazing angle of incidence. Incident at a grazing angle of incidence, I1. It then gets reflected from M1, and this angle, by the way, will also be I1. This angle will also be I1, right? And then it gets reflected once again. And now this grazing angle is I2. So for this reflection, this grazing angle will also be I2, Clear? Similarly, it gets reflected again, and so on and so forth, Multiple reflections. Alright. Now, we want to compute the total deviation in n reflections. We want to compute the total deviation in n reflections. Now, for the first reflection, what's the deviation delta 1? 2i1 in magnitude, but clockwise, yes or no? In the absence of the mirror, the ray would have travelled like this, but now it's travelling this way. So the deviation is clockwise, and therefore the algebraic deviation delta 1 out of the first reflection is going to be minus 2i1. That's the algebraic deviation in the first reflection. Got me? In the second reflection, realize that in absence of this mirror M2, the ray would have gone this way. The ray would have proceeded like this, but now it's going this way. So now the deviation is anti-clockwise. So then it will be plus 2i2. Similarly, let's say this is I3. I1, I2, I3, etc. The deviations would alternate in signs. The third deviation you'll figure out is of an opposite sign, minus 2i3, and so on and so forth. The nth deviation. So, we do not know n, but in any case, delta 1, delta 2, delta 3, delta n deviations produce clockwise, anti-clockwise, clockwise, anti-clockwise, and so on and so forth. Right? Now, we need to, I1 is known to us, and theta is known to us. So, we want to be able to compute the total deviation entirely and exclusively in terms of I1 and theta, the angle between the two mirrors and the original raising angle of incidence I1. Alright. Now, simple geometry. Look at this. I2 would be I1 plus theta. Exterior angle is sum of two interior opposite angles, right? I2 is I1 plus theta. Right? Similarly, I3 would be I2 plus theta. And then next I4 that you are going to get would turn out to be I3 plus theta. And In would turn out to be In minus 1 plus theta. So then Ik constitutes a progression. What's the nature of the progression that Ik constitutes? Arithmetic progression. It's an arithmetic progression. To obtain I3, to obtain I2, you need to add theta to I1. To obtain I3, you need to add theta to I2. So these IKs constitute an AP, yes or no? That's how an AP was defined. Right? What's the common difference of this AP? Theta is the common difference of the first term of the AP is I1, the common difference is theta. So then this constitutes an AP with common difference theta. So then in general, In would be I1 first term plus n minus 1 into theta. In would be I1 plus n minus 1 into theta, yes or no? Right? I2 would be I1 plus theta, I3 would be I1 plus 2 theta, and so on and so forth, right? In general, In would be I1 plus n minus 1 into theta, I2 would be I1 plus theta, I3 would be I1 plus 2 theta, I4 would be I1 plus 3 theta, and so on and so forth, right? Now, once this comprehension dwells upon you, we can find the algebraic deviations. Delta would be minus 2i1 plus 2i2 minus 2i3 up to how many terms? N terms. For n deviations, for n reflections, n terms of this, right? Which would be minus 2 times I1 plus 2 times I2 is like a I1 plus theta. I3 would be I1 plus 2 theta. Similarly, I1 plus 3 theta up to n terms, Which would then turn out to be, let me club together the I1 terms and the theta terms in two groups, the I1 group and the theta group. So then the I1 group is minus 2I1 plus 2I1 minus 2I1 plus 2I1. How many such terms? N terms, right? And then the theta terms put together, 2 times theta minus 2 theta plus 3 theta minus 4 theta plus how many such terms? N minus 1 terms. The theta terms are starting from the second term to the nth term. So, n minus 1 terms, right? N minus 1 terms. Now, evidently, this summation would depend on the parity of n. That means whether n is even or odd, right? For example, when n is even, these would add up to 0 because they would get completely paired. So this will become independent of I1 when n is even. However, when n is odd, then they would be a term that would not cancel off because they are not completely paired, right? So let's do a calculation for n even and n odd. Let's compute delta, the deviation for n even and n odd. Case 1 when n is even. When n is even, the number of pairs are n by 2. Number of pairs are n by 2 and each pair adds up to 0. However, when n is even, n minus 1 is odd. N minus 1 is odd, yes or no? Now, if I isolate the first term, then how many terms do we have? N minus 2 terms. And that's even, right? That's even. So now, these terms, except, look, forget the first term. If you forget the first term, the number of terms are n minus 2, which is even, right? So then, those terms completely get paired. Minus 4 theta plus 5 theta. So each pair adds up to theta. We have how many pairs? Except the first, we have n minus 2 by 2 pairs. Forget the first one. How many pairs do we have? N minus 2 by 2. And each pair adds up to theta, right? So then, we have twice theta, which is unattended, and then the number of pairs are n minus 2 by 2, and each pair adds up to theta. Each pair adds up to theta. Right? Which then turns out to be n theta. When n is even, it turns out to be n theta. Because see, this theta gets cancelled, simply this n theta into 2, etc. Pardon me? Case 2 when n is odd. Case 2 when n is odd. When n is odd. Okay. Now the deviation here. Realize that when n is odd, n minus 1 is even. When n is odd, n minus 1 would be even. So now in this first group, if I isolate minus 2I1, we have complete pairing taking place and each pair adds up to shunya. So then we have one isolated term which is minus 2I1. Yes or no? Right? So this is like a minus 2I1. And right here, we have n minus 1 terms which is even. right? Now we have an even number of terms and therefore a perfect pairing occurs, and each pair is like a minus theta. Each pair is like a minus theta. See, minus theta, and so on and so forth. How many pairs? N minus 1 by 2, right? And each pair is like a minus theta. Got me? So then, and of course there is a into 2. There is a this 2. I'm so sorry, I missed out this 2. There is a into 2 here. This 2 that was sitting quiet. So then this is like a minus 2i1 minus n minus 1 into theta. Then n is odd. Now this depends on I1. This depends on I1. When n was even, it was independent of the initial grazing angle. But then when n is odd, it depended on the initial grazing angle of incidence. Got me? Now, another result which finds useful applications suppose this is a plane mirror M. There is an incident ray IR. There is an incident ray IR. This is a normal at the point of incidence. N1. Initial normal. Initial normal at the point of incidence. This is the reflected ray. We call it RR1. This is called reflected ray 1. This is I, angle of incidence. This is also I, angle of reflection. Both are equal, right? Now, one thing, if I have a mirror M, and this was the normal at a certain point N1. Now, if I rotate the mirror by a certain angle theta out of its plane, if I rotate the mirror by an angle theta out of its plane, realize that the normal will also rotate by the same angle theta. The new normal, that is N2, the new normal N2 for this new position of the mirror would enclose an angle theta. Angle between the two normals at the point P would be theta, right? And now, see, if this was an incident ray, right? Then if the initial angle of incidence was I, then the final angle of incidence will not be I, it would be I plus theta, because this is the new normal. The incident ray will not change its direction because the mirror moved. The incident ray does not know, it just knows the point P. When it strikes P, it identifies the normal and gets reflected commensurate. This would become the new reflected ray. This would become the new reflected ray in the new position of the mirror. Yes or no? So, if the new angle of incidence is I plus theta, the new angle of reflection would be I plus theta. Yes or no? This would be the new angle of reflection, which is measured to the new position of the normal, which would be I plus theta. Make sense? So then, what I propose doing is, can I remove the clutter from here? let me rotate the mirror by an angle theta and observe the new reflected ray. The incident ray will be the same. The new reflected ray is what I am seeking. Okay. So when I rotate the mirror by an angle, this was the mirror, let's say mm prime, and I rotate the mirror by an angle theta, basically then I am arriving at a new normal. I am arriving at a new normal. This is the new normal. N2. Final normal. This is the new normal, the final normal. If the mirror has been rotated by an angle theta, the normals also rotate by an angle theta. The normal has rotated by an angle theta. Yes or no? Clear? So then, for this new position of the normal, which would correspond to a new position of the mirror, which has got reflected by an angle theta with respect to the original position. The new reflected ray is this thing. Let's say this is the new reflected ray, RR2. Same incident ray. When the mirror was like this, the normal was like this, and this was the reflected ray. When the mirror got rotated by an angle theta, this became the new normal. This remained the incident ray. However, the reflected ray now rotated commensurate with the new position of the normal. Got me? Now, the new angle of incidence is I plus theta. Do you realize that? The new angle of incidence is I plus theta. This is the incident ray. This is the new normal at the point of incidence. So, the new angle of incidence is I plus theta, and therefore, the new angle of reflection would be new normal, and the new reflected ray must also be I plus theta. Would be the new position of the normal, new position of the reflected ray. The new angle of incidence is I plus, angle of reflection is I plus theta. Okay. Now, what is this angle? This is theta, this is I. So, this angle that I have shown here is theta minus I. This angle is theta minus I. Now, this was the original reflected ray. This was the final reflected ray. Yes or no? This was the original reflected ray. This was the final reflected ray. Now, the angle between the original reflected ray and the final reflected ray is how much? Theta minus I plus theta plus I, that's 2 theta. So, angle between RR1 and RR2, angle between RR1 and RR2 would be 2 theta. Angle between RR1 and RR2 is 2 theta. That means the reflected ray has got rotated by an amount 2 theta. So, if the mirror is rotated by an angle theta, the reflected ray rotates by twice that angle. If the mirror rotates by an angle theta, the reflected ray rotates by twice that angle. If the mirror has rotated by 15 degrees, the reflected ray for a given incident ray would rotate by an angle 30 degrees. The reflected ray would rotate by an angle 30 degrees, and so on and so forth. Right? That's a very important result. Very useful for MCQs. There would be very cute looking applications built around this result. Okay. Now, it's not that this would always hold good. It's not like each time you rotate the mirror by an angle theta, the reflected ray would rotate by an angle twice theta. Tell you how it happens. Suppose this is the mirror and this is the incident ray. Suppose this is the arrow, this is the incident ray. Alright. If I rotate the mirror by an angle theta like this, the reflected ray, which was originally like this, will get rotated by twice that angle. Right? If I rotate the mirror like this. However, if I rotate the mirror like this, will anything change on the reflected ray? So, the mirror has to go out of its plane. If the mirror is rotated in its own plane, then nothing will happen to the reflected ray, because the normal at the point of incidence remains the same. See, if I rotate the mirror like this in its own plane, then there is no change in the reflected ray. Only when the mirror is rotated out of its plane will the reflected ray rotate by twice the angle by which the mirror has rotated. Got me? So, that's a point that you must remember. Can I wipe this off? Now, it's important, before we get into a detailed digression on geometrical optics, it's important that we understand the concept of an image. Concept of an image. So write down. If rays of light starting from a certain point after reflection or refraction, actually converge to a second point, then the second point is referred to as the real image of the first. And the second point is referred to as the real image of the first. If, however, after reflection or refraction, they appear to diverge from a certain point, then that point is referred to as the virtual image of the first. At the point where there actually is a real image, there would be intensity of light, because of energy confluence. At a point where there is a virtual image formation, energy does not confluence, and the concept of image, is kind of notional, N-O-T-I-O-N-O-L, notional. Now, for example, suppose this is a certain reflector. For example. And there is a point P, illuminated point P, which is referred to as an object. This is an illuminated point P, which is an object. Now, to constitute the image of a point object, this is a point object. To constitute the image of a point object, you would have to look at two incident rays, and the corresponding reflected or refracted rays, as the case may be, right? An image could be formed because of reflection, or it could be formed because of refraction. So, to constitute the image of P, any two incident rays, and therefore the corresponding reflected or refracted rays would suffice, right? Any two incident rays. So, if this is one incident ray, IR1, and this is another incident ray, let's say IR2, and after reflection, let's say this is reflected ray 1, and this is reflected ray 2, realize what the figure depicts is that the two rays after reflection are actually converging to a certain point P prime, There is light energy at P prime. Then this is the real image of the object P. Point object P. If, however, this is P, an object, and I took an incident ray 1, and we took incident ray 2, and the following happened. This was reflected ray 1, this was reflected ray 2. Realize that the reflected rays here, after reflection, they're not converging to a certain point. We still have to talk of an image of P. But then in this case, we don't talk of real image. We talk of a notional image, which is the virtual image, because after, they do appear to diverge from a certain point. A certain point P prime. These two rays, they're not converging to any point, but if there is an eye here, then these two rays, as far as this eye is concerned, these two rays seem to, I'm so sorry. Two reflected rays, right? These two reflected rays seem like coming from P prime for this eye, but there is no light energy at P prime, right? Light had actually nothing to do with P prime. So this P prime is not the real image for this eye. This eye would report an image. What image would it report? It would report P prime as the image. It would think that these rays of light, these reflected rays, are coming from P prime. These reflected rays are coming from P prime. So P prime is then said to be the virtual image of P. P prime is then said to be the virtual image of P. But then, do you associate any light energy with P prime? No. I mean, there is no prevalence of, there is intensity of light which got reflected, which never settled at P prime. There was no light at P prime actually. But just the fact that the two reflected rays seemed like coming from P prime as far as this eye was concerned. Right? So this eye said the image is actually at P prime. Right? So this is the virtual object for P. This is the, virtual image for P. Virtual image for P. Got me? Now, the way we can have a real, so you understand the notion of a real image and a virtual image. The way we have the notion of a real image and a virtual image, we also have the notion of a real object and a virtual object. A real object and a virtual object. Sorry? Then we say that the image is at infinity. The virtual image is at infinity. The image is there, it's at infinity. We say that the image is at infinity. Very simple as that. That's what we say. Mathematically, that's the statement. I mean, his question is, what if these two rays are parallel to each other? Then these rays intersect at infinity. These rays intersect at infinity, that's what we say. Now, so the question of a real image and a virtual image. Settled, right? We understand a real image and a virtual image. Now, the question of a real object and a virtual object. Right? The question of a real object and a virtual object. Look, maintain this figure because I'll just use this very thing. We'll not reinvent the wheel. Now, suppose these reflected rays are intercepted by a plane mirror. These reflected rays are intercepted by a plane mirror, right? Now, for this plane mirror, P prime is the object. P prime is the object for the plane mirror. P prime becomes an object for the plane mirror. It's actually a source of energy. It's actually a source of energy. For the plane mirror, we have an illuminated point P prime. We have an illuminated point P prime. This P prime, which actually sends out energy, to the plane mirror, is actually for the plane mirror a real object. A real object. It was a real image for P, but now for the plane mirror, it turns out to be a real object. From where light is actually going out and is being intercepted by the plane mirror. Right? Then the mirror forms an image of P prime, and you know object distance is image distance. The image of P is formed at P double prime such that object distance is equal to the image distance. Object distance equals the image distance. So this becomes a real object. This becomes a real object for image formation by this plane mirror. For image formation by this plane mirror, this becomes a real object for image formation by plane mirror. Image formation by the plane mirror, this becomes a real object. A real object would really send out energy, light energy, right? It would actually be an illuminated point from where light energy would go out, travel in different directions for the sake of image formation, could be intercepted by a reflector or a refractor. This is a real object. In contrast, can I just remove this clutter? Do you understand what a real object is therefore? Right? In contrast, if these two RR1 and RR2 had to be intercepted by a plane mirror, for example, there is light energy falling on the plane mirror. So the plane mirror would have to create an image out of these light rays, and for it to create an image out of these light rays, it would have to identify the object. So its object here would be P prime, because this plane mirror would think that these rays are coming from P prime, where P prime is actually not an illuminated point. There is no light energy at P prime. Do you realize that? At P prime there is no presence of light because of the reflected rays. It's notional. But for the plane mirror, when these rays intersect the plane mirror, then the plane mirrors would cause these rays to either converge or diverge, right? So then it would have to identify, for it to form an image, it would have to identify the object. What would the plane mirror think is the object? It would think that P prime is the object. The plane mirror would think that the object is P prime. P prime becomes an object. But now, is this a real object or a virtual object for the plane mirror? It's a virtual object, right? So this P prime becomes a virtual object for plane mirror. This becomes a virtual object for the plane mirror. So you understand the concept of a virtual object and a real object? Concept of a virtual image and a real image? Yes or no? Can I wrap this off? See, if we had a plane mirror like this, there was a point object P, and you understand that its image is formed at P prime. Incident ray 1, reflected ray 1. This was incident ray 2 and reflected ray 2, right? Any two incident rays and the corresponding reflected rays would come together . Little bit of a badly drawn figure. I'll redraw it so that you're not confused. I'll just redraw the figure. I don't want to add confusion. Object P, and we know image is P prime. I'm just doing a backward calculation in the sense, so that geometrically it fits. Incident ray 1. Incident ray 2. This is reflected ray 1 and this is reflected ray. So these rays, after suffering reflection from the mirror, they appear to diverge from the point P prime. P prime is the virtual image of the point P. This is the real object, whereas this is a virtual object, and enjoying properties like object distance equals image distance and so on and so forth, right? So any two reflected rays will appear to diverge from the point P prime. This is the virtual object, virtual image. This is the virtual image of the real object P, In contrast, suppose This was the plane mirror. And there was a beam that was incident like this. There was a converging beam coming from somewhere. There was a converging beam coming from somewhere, incident on a plane mirror. Then after reflection, this is what happens, right? This converging beam after reflection settles at some eye, which is the image, right? After reflection, these two rays, the converging beam, would settle at eye. So if eye is the image, the question is, the mirror treated something like an object. What was the object? The object must have been this. The object for this image formation is this. This is the object. But what kind of an object is this? It's a virtual object. It's a virtual object. And this is a real image. By the way, this is a real image. So a plane mirror could constitute a virtual image as well as a real image. Both are possible. And the object image, because of the principle of reversibility of light, enjoy a conjugate relationship in the sense that now if this was an object and rays of light went this way, then O would be its virtual image. See, if this was a real object, then principle of reversibility means this ray would go like this and would go this way, this ray would go like this and would travel this way, and after reflection they would appear to diverge from O. Then O would be the virtual image of the real object. So object and image in geometrical optics, owing to principle of reversibility of light, enjoy a conjugate relationship, an interchangeable relationship, right? Got me? So you understand the notion of the object and image, both real and virtual. Clear? Now, one more result which is pretty relevant to geometrical optics, especially for an examination, very useful, is let's say there's a man of a certain height and he wants to see himself completely. What's the size of the plane mirror? So all of you know this. Can you prove this result also? Can you all prove this result? I'll quickly tell you. It's so easy to, very ordinary geometry. You know, if this man is of a certain height, then the minimum size of a plane mirror that is required so that he can see himself completely is half. You can see, because suppose this was the mirror. This was the man AB. This is where his eye is. Now, if his eye can see a reflected ray from A and can see a reflected ray from B, then he can see himself completely, right? And let's say at the extremity, incident ray coming onto the eye, the incident ray from B again falling in. That means the man can see A because of this ray and can see B because of this ray, right? Then he can see himself completely in the mirror. If he can see his end points, then he can see himself completely. So this angle is alpha, this angle is also alpha, this angle is beta, this angle is also beta because of laws of reflection. And if this length is x, this length is y, again realize that this angle is alpha, this angle is beta, alternate angles. So then if this is x, this is also x, this is also x, and these two triangles are congruent, congruent. So this is also x. Similarly, if this is y, this is y. And again, this triangle is congruent to this triangle, causing this to be y. Right? So the height of the man is 2x plus 2y. AB is 2 times x plus y. Size of the mirror is x plus y. Size of the mirror is x plus y. So the minimum size of the mirror for the man to see himself completely must be half his own height. Half his own height, right? Right, Agnish, can I wipe this off? Again, if this is a mirror, and there is a wall AB, this is a wall AB, and there is a man standing exactly halfway between the wall and the mirror. There is a man standing exactly halfway between the wall and the mirror. The man exactly halfway between the wall and the mirror. And he wants to be able to see the wall completely through the mirror. He wants to be able to see the, let's say this is the eye of the man, and he wants to be able to see the wall completely. Assume. Then a ray from A, the upper end of the wall, must be witnessed by E. That means a reflected ray should fall on the eye for him to be able to see A. The reflected ray must fall on the eye. Again, notice that this angle alpha, 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 say this is x, this is x, this would be x, EP would be x, and now PMN. But you realize that triangle AMD, triangle AMD is similar to triangle EPD, because angle alpha, alpha, 90 degrees, 90 degrees. So AMD similar to triangle EPD. All angles are equal, right? And this distance is small d, whereas this distance was 2d. This is small d, this was 2d. That means the ratio of their sides is 2. Ratio of their sides is 2. That means if this is x, this must be 2x. These triangles are similar and the ratio of their sides is small is 2. Right? Ratio of their sides is 2. Right? Because this is 2d and this is d. So if this is x, this must be 2x. AM is 2x. This is x. Right? So then NA is 3x. NA is 3x. NA is 3 times x. Similarly, look at the point B. See, this is Y. This is Y. And the manner in which we got NA as 3x, we should get NB as 3y. NB in exactly the same manner would turn out to be 3 times y. See, NA is 2x plus x, 3x. So, NB would turn out to be 3 times y. Exactly the same geometry, right? So then, the size of the wall is 3 times x plus y, whereas the size of the mirror is x plus y. So then the mirror is 1/3 the size of the wall. The mirror is 1/3 the size of the wall, right? The mirror is 1/3 the size of the wall. You can see. So if there is a man standing exactly halfway between the mirror and the wall, the minimum size of the mirror required is 1/3 the size of the wall. However, if the man changes position, then the ratio of these sides will not be 2, would change. Then the size of the mirror compared to the size of the wall would be no longer 3, would be something else. Right? So, the standard result is, if he is standing halfway between the mirror and the wall, then the size of the mirror, the least size of the mirror is 1/3 the size of the wall. If he is standing somewhere else, then you will have different ratio for these sides, then depends on where he is standing. Clear? Stand by. Alright, next I am going to look into reflection on curved surfaces. Reflection on curved surfaces. Now again, this could be very open-ended. The curved surface could be of so many kinds, but the one that we will focus on is what we refer to as a spherical curved surface. Can you switch this off? Do we actually need this? Because it's very noisy. So a spherical curved surface then, if you have a sphere, this is the center of the sphere O. Center of the sphere O, or call it C. Center of the sphere, call it C. The sphere has a certain radius. The sphere has a certain radius. The tangent at any point of the sphere, if this is the tangent at any point of the sphere, then the radius at the point of tangency would be perpendicular to the tangent. The radius at the point of tangency would be perpendicular to the tangent. So the radius at any point of this curved surface, would be a normal to the curved surface, Why? Because it's perpendicular to the tangent to the curved surface, right? So if you draw any radius, any line passing through the center of the sphere, then that line would be a normal to the surface. That line would be a normal to the surface at the point where it intersects the surface. Clear? Now, this sphere could be cut. For example, it could be cut this way, Mn. Let's say this portion is cut out, Mn is cut out. C is the center of the sphere. Now, when you cut this portion Mn out, it's part of the bigger sphere. It's part of the bigger sphere. So then this surface is a spherical surface. It's not a full sphere, but it's spherical in character. The radius at every point of the surface is still r. The radius at every point of the surface is still r. Even if you cut this and just use this portion, this is spherical in character, and this is part of a sphere. This is part of a sphere whose center is C and whose radius is r. Whose radius is r. Now, two possibilities. This Mn can be silvered on the bulging portion, could be silvered on the bulging portion, and the portion that is inside could be used as a reflector. The portion which is inside could be used as a reflector. When you do that, then the mirror formed is a concave mirror. Mirror formed is a concave mirror. However, if you silver the inside portion, then the bulging portion is the reflecting surface. This is the reflecting surface. In this case, the bulge is the reflector. In this case, this is the reflector. So the reflector could be outside or the reflector could be inside, depending on where the surface is silvered. If it's outside like this, then it's called a convex mirror. It's called a convex mirror. And that's a concave mirror. That's a concave mirror. So, be it a concave mirror or a convex mirror or a concave mirror, both are part of a bigger sphere. Both are part of a bigger sphere. Alright. This portion Mn is called the aperture of the mirror. This Mn is called the aperture of the mirror. Be it this or that, Mn is called the aperture of the mirror. Mn is called the aperture of the mirror. The midpoint of Mn, P is the midpoint of Mn. That's referred to as the pole of the mirror. That's referred to as the pole of the mirror. The center of the sphere, C, of which the mirror forms a part. The center of the sphere of which the mirror forms a part, that is the point C. See, this mirror forms a part of a bigger sphere. Its center is somewhere here, right? This center C is called the center of curvature of the mirror. It's called the center of curvature of the mirror. Right? A line passing through the pole and the center of curvature, a line passing through the pole of the mirror and the center of curvature of the mirror is called the principal axis of the mirror. A line passing through the pole and the center of curvature of the mirror, that line is referred to as the principal axis of the mirror. Now, the geometrical optics that we would deal with would be one where we would look into a paraxial ray treatment. A paraxial ray treatment. We would look into the geometrical optics of paraxial rays. We would look into the geometrical optics of paraxial rays. Now, what is it that I mean by a paraxial ray treatment? Suppose this is a mirror. Pole P of the mirror, and let's say this is an object O. This is an object O. We would look into image formation by the mirror. For rays that start from O, and are incident very close to P. The point of incidence, M, is very, very close to P. Very, very close to P. This M is very, very close to P. MP is practically zero. Rays incident on the mirror extremely close to the pole. How can you ensure that happens? You can ensure that by selecting mirrors with very small apertures. If the aperture of the mirror itself is very, very small, then the farthest it could be from the pole is still small enough, right? If the aperture of the mirror itself is very small, right, then the farthest ray of light can hit the mirror is this extremity, at one extremity of the aperture, that itself would be small. If Mn, the aperture is small, then this point of incidence would be still close enough to the pole of the mirror, right? First. Second, all angles theta involved are very small. That means the angle of inclination of rays with the principal axis, write down, the angle of inclination of rays with the principal axis, in brackets write incident or reflected, would be extremely small. So these angles would be really small. Even if this is a reflected ray, then this angle theta prime would also be very small. Theta prime, etc. If this is a reflected ray, this angle theta prime would also be very small, right? So two things about the paraxial ray treatment. Number one, the mirror should be of small aperture. So that any ray incident on the mirror is very close to the pole of the mirror, right? That's one. Number two, the angle of inclination of all rays with the principal axis must be extremely small. That's paraxial ray treatment. Right? Second thing. Sign convention. Now, the object and the image and other things would have to be located, right? So we need a reference for location of the object, image, etc. So to be able to locate the object image, we would need a origin or a reference point. The most suitable choice of the reference point from where distances are measured is the pole of the mirror. So all distances would be measured with respect to the pole of the mirror. Next, these distances would be algebraic. These distances would be algebraic. All distances measured from the pole would be algebraic. These distances are algebraic. When measured in the same direction as the incident ray, measured in the same direction as incident ray, it's considered positive. When distances are measured from the pole, by traveling in the same direction as the direction of the incident ray. For example, in this case, this is the direction of the incident ray, right? I'm sorry. This is the direction of the traversal of the incident ray. So from the pole, if I measure a certain distance in this direction, then that would be considered negative. Distances measured from the pole in the same direction as the traversal of the incident ray, this is the incident ray, then that distance would be regarded negative. Negative. Distances measured in the same direction as the incident ray to be considered negative. And opposite to the incident ray, the distance would be regarded positive. Opposite to the traversal of the incident ray, measured from the pole of the mirror, distances would be regarded positive. So for example, in this case, this is the object, and suppose this is 10 centimeters. Then the algebraic object distance would be plus 10 centimeters. Why? Because to locate the object, plus u, I'm moving in a direction opposite to the direction of the incident ray. So in this case, this location of O is plus 10 centimeters. Because moving in a direction opposite to the direction of the incident ray. That's the sign convention. All distances to be measured from the pole of the mirror as the reference. When you move in the same direction as the incident ray, it would be regarded negative. Opposite to the direction of the incident ray, it would be regarded positive. Right? Got me? Now, so even if you have learned some geometrical optics from here and there, and if you have embraced some other sign convention, the first thing that you need to do is dump that sign convention. Embrace the one that I have stated a little while ago. You need to forget all other sign conventions that have come to you if you have learned geometrical optics in school or otherwise. Okay, so this is the one that we would follow all the time. All right. Although the sign convention does not alter the physics, but then it does give you a new look to the mathematics of the problem. All right. So I see merit in this sign convention, and this would be in stark contrast to the sign convention that you would read in books or the one that would be taught in school. But this is the one that I very strongly recommend. All right. So this sign convention, that far and no further. So now let's look at some relationships between object distance, image distance, and the geometry of a spherical mirror, First of all, let me tell you that U would be referred to as an algebraic object distance. Algebraic object distance V would be referred to as an algebraic image distance, and R would be, see, radius of the sphere of which the mirror forms a part is the radius of curvature. Did I tell you that? Is the radius of curvature. And the center of the sphere of which the mirror forms a part is the center of curvature of the mirror, right? So R will be the algebraic radius of curvature. R would be the algebraic radius of curvature. So they would come married to signs. U, V and R would have their signs. They are algebraic. if u is measured by traveling in a direction same as the incident ray, negative, opposite to the direction of incident ray, positive, same with v and r. Alright. So, let me look at a plane mirror, a concave mirror of this kind, concave spherical mirror of this kind. This is the pole of the mirror, an object O. Now, again, paraxial ray treatment, the image would be a paraxial image, and to locate the image, you need any two rays would bring out the image. The center of curvature is C here of this mirror, the center of curvature is C. This is an incident ray. How do I draw the normal at the point of incidence? If I just join A to C, then that would be the normal at the point of incidence, right? The radius at A of the sphere would be the normal at the point of incidence, right? So then AC becomes the normal at the point of incidence. This then would be the angle of incidence I. This would be the angle of incidence I. And this is a certain reflected ray. So then this becomes the angle of reflection, which is also I. Angle of reflection, which is also I. Now, this is one reflected ray. I need one more reflected ray to get the image of O. So, the other rays, convenient ray that you can imagine is one going like this, hitting P. This incident ray, when it passes through C, is incident normally on the mirror, right? Realize that this ray is incident normally on the mirror. So, angle of incidence is 0. So, angle of reflection will be 0. So, any ray of light which passes through the center of curvature would retrace its path, right? So, then this is the reflected ray. And now, two reflected rays, this reflected ray and this reflected ray, they intersect at this point I. Then this point I should be referred to as the image of O. For the figure that I have drawn, what kind of an image is I? Real image. What kind of an object is O? Real object. Alright. However, the relationship that we are going to arrive at would be true irrespective of whether the object is real or virtual, or whether the image is real or virtual, because of the principle of reversibility, right? So the relationship would be true for all, but then this is for this particular case, we would arrive at a relationship between object distance, image distance, and the radius of curvature for the mirror. All right. Now, say this angle is alpha, this angle is beta, and this angle is gamma. All right. This I is alpha minus beta. This I, interior angle is alpha minus beta, right? And this I would be beta minus gamma. This I would be beta minus gamma, right? See, this I is alpha minus beta. This I is beta minus gamma, right? Which gives us like a alpha plus gamma is 2 beta. Alpha plus gamma is 2 beta. Okay. Now, alpha, beta, gamma are really small angles. Alpha, beta, gamma are really small angles. That's paraxial ray treatment, right? Alpha, beta, gamma are really small angles. So, if these angles are small, if a certain angle theta is small, then theta is practically the same as tan theta is practically the same as sin theta. When theta is really small, tan theta, theta and sin theta are almost equal. Given that theta is in radians, then theta, tan theta and sin theta are almost equal. So then, if that be the case, then alpha can be replaced by tan alpha, beta by tan beta and gamma by tan gamma if alpha, beta, gamma are really small angles, right? So then doing so, you end up getting tan alpha plus tan gamma is 2 times tan beta. Yes or no? Replacing alpha, beta, gamma by tan alpha, tan beta, tan gamma on the premise that these are small angles, they are replaced by their corresponding tangents, right? Now from A, you drop a perpendicular, call it AQ. Drop a perpendicular, call it AQ on the principal axis, PA. Then what's tan alpha? Tan alpha is AQ by QI. Tan alpha is AQ by QI. Tan gamma is AQ by QO. Tan gamma is AQ by QO, right? Tan beta is AQ by QC. Right? Now, realize that since A and P are very, very close to each other, paraxial ray, this PQ is practically zero. Since A and P are very close to each other, this PQ should be very, very small. No, Rajat. And if that be the case, then whether you measure distances from Q or you measure distances from P, they'll be the same. So a QI could be replaced by a PI, a QC could be replaced by a PC, and a QO could be replaced by a PO, right? So then replacing QI, QO and QC by PI, PO and PC, you get AQ by PI plus AQ by PO is twice AQ by PC. Yes or no? Now, if U, V and R are algebraic object distance, algebraic image distance and algebraic radius of curvature, then realize that Pi is a length only. It's only greater than 0. Pi, PO and PC are all positive numbers. These are lengths. I mean, tan of this is this length divided by this length. So AQ, PI, AQ, PO, AQ, PC, these are all positive numbers. These are only lengths. Right? There is only trigonometry. There is no sign involved here. Right? Pi is magnitude of image distance. If V is algebraic image distance, V could have been positive as well as negative, depending on where the image is. V could have been positive as well as negative. There is a possibility that the image may have been formed here. If the image was formed here, then Pi would have been positive, but V would have been negative. Right? So V could be positive as well as negative, but Pi is only positive. Pi is a length, distance between P and I. That's Pi. Whereas V is algebraic image distance. So then, can I say that the length Pi is actually magnitude of the image distance? Can I say that the length Pi is magnitude of the image distance? These bars will cause the sign to get obliterated, leaving it with a positive sign, right? V is algebraic, but Pi is not algebraic. Pi is a length, right? V can be positive or negative, but Pi is always positive. Pi is algebraic image distance, right? Similarly, PO is algebraic object distance. Object could have been, U could have been negative because, there could have been a virtual object. For example, if this was a mirror, you could have had a converging beam like this. In the absence of the mirror, it would have converged to a point O here. And this would have been a virtual object. Right? For image formation by the mirror. See, we could have had something like this. A converging beam on the mirror. And O then would be a virtual object, not a real object. Right? Image could have been formed somewhere here, for example. So in this case, U would be negative. Why? Because this is the direction of the incident ray. Whereas to locate O, you're still moving in the same direction as the incident ray. So U would have been negative. So U can be positive as well as negative. But the length PO is only positive. So PO is magnitude of the object distance. Magnitude of the object distance. And similarly PC. PC would always be positive. Right? But R can be positive as well as negative. How could it be negative? Instead of a concave mirror, you could have had a mirror which is convex, because this is a convex mirror. This is a convex mirror. Pole P. Now this is part of a sphere which is like this. Part of a sphere which is like this. The center of that sphere is located here. So the center of curvature of this mirror is here, right? And now, if this is the incident ray, this is an incident ray. If this is an incident ray, then to locate the center of curvature, you have to move in the same direction as the incident ray. From the pole, you got to be moving in the same direction as the incident ray. So in this case, R is negative. R is negative. So R could have been positive as well as negative depending on the nature of the mirror. Depending on the nature of the mirror, it could have been positive as well as negative. So then, PC however is just a length. So it should be magnitude of R. Magnitude of R. So the relationship, realize that depending on the sign of R, the mirror could be looked upon as a concave mirror or a convex mirror. So we don't have to derive different relationships for convex and concave mirror. Just a suitable sign would cause the mirror to be concave or convex. So the relationship that we are going to arrive at would be true, be it a concave mirror or a convex mirror. It's just the sign of R which will help you toggle from one kind of mirror to the other kind. Got me? Right? So, I write AQ gets cancelled, PI written as mod V, PO written as mod U, and PC written as mod R. Right? Now for the figure, let me reduce it for the figure. In this case, V is positive or negative? Positive. Why? Because I am moving opposite to the direction of the incident ray. So if V is positive, then mod V would be equal to V. Mod V would be equal to V if V is positive, right? Mod U would be equal to U if U is positive. Why? Because to locate the object, again I am moving in a direction opposite to the incident ray. So U is positive, so mod U would be U. Similarly, to locate the center, I am moving in a direction opposite to the direction of the incident ray. So for the figure, R is positive. So mod R would be equal to, right? So then replacing mod V, mod U, mod R by V, U, R, you get like a 1 by V plus 1 by U is 2 by R. A relationship between algebraic object distance, algebraic image distance and the algebraic radius of curvature for a mirror, concave or convex. Yes or no? Simple, right? Just for the heck of it, let me just, to make yourself mentally comfortable, quickly draw the same thing for a convex mirror. You realize that the algebraic relationship that you arrive at would be the same. See, if we had not, why is it that we look upon U, V and R as algebraic? If we had not done so, then for each mirror, each kind of mirror, you would have had to arrive at a different formulation. But now, the fact that U, V and R are algebraic, the same relationship would be, you would expect the same relationship to come up even for a convex mirror. Because it's just the sign of U, V and R which you can plug in based on the nature of the mirror. So let me quickly tell you a derivation, similar derivation for a convex mirror. I hope all of you have understood this. 1 by V plus 1 by U equal to 2 by R for a concave mirror. Let's say this is a convex mirror, pole of the mirror. Objective, one incident ray, let's say this was the center of curvature of the mirror, right? The center of curvature of this mirror would lie here, because conceive a sphere like this. So the center of the sphere would lie here. So the center of curvature of this mirror would lie somewhere here, right? The normal at the point of incidence would be this. This is the normal at the point of incidence. This is the normal at the point of incidence, right? This then would be the reflected ray. This then would be the reflected ray. You need two reflected rays, right? You need two reflected rays. This is one reflected ray. Now, the other incident ray could be like this. Now, this incident ray passes through C. So, angle of its incident normally on the mirror, its incident normally on the mirror, angle of incidence is 0. So, angle of reflection would be 0. The reflected ray retraces its path, right? The ray retraces its path. So, then two reflected rays. One is this, the other one is this. They're diverging. From which point? If there is an eye here, the eye would think that the two reflected rays, this one and this one, are coming from a certain point, I here. So, I then turns out to be the image of O. But what kind of an image is it? Virtual image. This is a virtual image, right? You see, there is no prevalence of light here. And I would just notionally think that these reflected rays are coming from this point I. Right? So, I is a virtual image here. So, then suppose this is A, the point of incidence is A here, and like before, let's say this angle was alpha, this was beta, and this was gamma. Alpha, beta, gamma are all very small angles, given that we are dealing with paraxial rays, right? See, in general, if it's a big mirror of a huge aperture, then there would be one image which would be the paraxial image. But then there would be other images that are non-paraxial images. For rays of light that are incident very far from the pole of the mirror, they would converge at a different point. They would constitute another set of images, but we are not looking at those images. We are only looking at that one paraxial ray image of a certain object. Alright. Now, this angle is I, angle of incidence. Normal at the point of incidence, incident ray. So, angle I, angle of incidence. Angle I, angle of incidence. Right? Now, vertically opposite angles. This angle is also I, this angle is also I. Is it visible to people sitting in the rear? This is I, this is alpha, beta, gamma, I, right? Then geometry. This I is what? Alpha minus beta. This I is alpha minus beta, right? And look at this I. That's going to be gamma plus beta. Can I say? See this exterior angle I. This exterior angle I is gamma plus beta about it. Right? So, is gamma plus beta. Make sense? So, we end up getting alpha minus gamma is 2 beta. Alpha minus gamma is 2 beta. And again, alpha, beta, gamma are small. So replace alpha by tan alpha, beta tan beta, and gamma by tan gamma. You end up getting tan alpha minus tan gamma is 2 times tan beta and like we did before, from A, drop of perpendicular AQ, drop of perpendicular AQ, then tan alpha would be AQ, the length AQ divided by the length QI, but the length QI is the same as length PI, so tan alpha is AQ by PI. Minus tan gamma. Tan gamma is AQ by QO, but QO is practically the same as PO. To tan beta. Tan beta is AQ by QC, which is the same as PC. AQ will get cancelled from both sides. PI, PO, PC are lengths. They are positive. They are positive. PI, reckon, is magnitude of image distance, not V, but magnitude of image distance, PI, so mod V, right? And PI, PI. PO is magnitude of object distance. PO is magnitude of object distance. And PC is magnitude of radius of curvature. So replacing PI, PO, PC by mod V, mod U, mod R, I get 1 by mod V minus 1 by mod U is 2 by mod R, right? Now, for the figure that I have drawn, to locate I, this is the incident ray, right? So this is the reference direction. This is the reference direction. To locate I, am I moving in the same direction as the incident ray from the pole? Yes. So V should be positive or negative? Negative. So if V is negative, mod V should be minus V. If V is negative, mod V should be minus V. So that minus V turns out positive, right? So then this mod V to be replaced by minus V. How about it? Right? Minus. Now, to locate the object, I am moving in a direction opposite to the direction of the incident ray. So U positive or negative? Positive. So mod U would be the same as U if U is positive, right? Now to locate the center of curvature, I am moving in this direction. I am moving in this direction. So regarded positive or negative? R negative, right? So mod R then should be minus R. Mod R then should be minus R. So then replacing V by minus V, U by U and R by mod R by minus R, sorry. So you get like a minus 1 by U equals minus 2 by R. So you get 1 by V plus 1 by U equal to 2 by R. Now obviously, it was redundant for me to have derived an equation for a concave mirror and for a convex mirror, given that R is algebraic. One way it would give me a concave mirror, the other sign of R would give me a convex mirror. It was useless to have done this again, since U and V were also algebraic. So a virtual object and a virtual image are all contained in this algebraic description. So I don't have to derive different formulas for different nature of object, image and the nature of the mirror, concave or convex. This should have been the same irrespective of the nature of the mirror and the nature of the object and the nature of the image, virtual or real. Alright, so 1 by V plus 1 by U equal to 2 by R is really the algebraic relationship between the object distance, image distance and radius of curvature for a spherical mirror. In fact, It's also true for a plane mirror. The same relationship is true for a plane mirror, because in a plane mirror, R is infinity. For a plane mirror, the radius of curvature of a plane mirror is infinity. And if you put R equal to infinity, you get V equal to minus U. That means mod V equal to mod U, but are of opposite signs. Realize that this is a plane mirror. This is a plane mirror. Its R is infinity. R for a plane mirror is infinity. This becomes the pole of the mirror. This is the object. So if the object distance U is 5 centimeters, the image distance will turn out to be minus 5 centimeters, right? So which would be 5 centimeters in this direction, right? So this is true even for a plane mirror. The plane mirror becomes a special case of a curved mirror with R equal to infinity. With R equal to infinity. Got me? So 1 by V plus 1 by U equal to 2 by R is the universal relationship for spherical mirrors, and as a special case also for a plane mirror. Now, for all mirrors, concave, convex, we have what's called the magnification produced by a mirror. Magnification, you would realize, is size of image divided by size of object. That's magnification, right? That's magnification. So, if an object of 20 centimeters has an image which is 30 centimeters, then the magnification would be 1.5, right? So, when I look at an object AB, for example, an extended object, for example, AB. Look at an extended object AB. Now, locate the image of B. Any two rays would clearly locate the image of B, right? So, for example, this is one ray. This angle is theta. This angle is theta. This is the reflected ray, right? So, the image must lie on any reflected ray. Would lie on any reflected ray, right? So the image of B, let's say, is somewhere here, which is B prime. The image of A is somewhere here, call it B prime. And the image of B is B prime, image of A is some A prime here. Image of A is some A prime here. Alright. So then what's magnification? Magnification is A prime B prime, size of image divided by size of object. That's magnification. That's magnification, right? So this is P, and these two triangles are similar. Do you realize? This angle is theta. This is also theta, angle of incidence equals angle of reflection. This is the normal at the point of incidence, right? So this triangle is similar to this triangle, because this angle equal to this is 90 degrees, this is 90 degrees, so this angle equal to this angle. So A prime B prime divided by AB will be the same as PA prime divided by PA. Similar triangles? This length divided by this length is the same as PA prime divided by PA, owing to similarity of the two triangles, right? So then this is PA prime divided by PA. P prime divided by PA. Hey, PA prime is what? Magnitude of image distance is magnitude of image distance. See, PA prime is magnitude of image distance, mod V, divided by PA, which is magnitude of object distance. That's the magnification. That's the magnification, or commonly referred to as the longitudinal magnification, because its magnification perpendicular to the principal axis. This is magnification perpendicular to the principal axis, commonly referred to as the longitudinal magnification. Longitudinal magnification, or just magnification. Some books would do some very unnecessary things. They would write magnification along with a sign. They would say V by U, algebraic V by U, and they would try and give meaning to a sign of magnification in terms of the nature of the image. That is bullshit. Don't even look at that prospect of assigning signs to magnification. In our scheme of things, in our blueprint, magnification would be deemed positive. Always ratio of the actual size of image divided by size of the object will not come married with signs. That's why these moduli are put up, so that the sign produced, the output of this is only a positive number, So if you're reading a textbook and they write like a V by U, and they sometimes say magnification is -4, and then the minus is given a certain, is interpreted in a certain manner, then kick its butt. Alright, that's not what we are going to adhere to at all. Magnification, positive, just the ratio of lengths, size of image divided by size of object, and that's all. Quickly go over this and I'll attend to you in another 5 minutes. Alright, so we derived a basic relationship for reflection on a curved surface. Now I arrive at something fundamental for refraction on a curved surface. Alright. So again, a curved spherical surface, it's going to have, when I talk of refraction, instead of one medium, you'll have a pair of media. So let's say this is a curved spherical surface separating two media, one of refractive index mu1, the other one of refractive index mu2. Curved spherical surface, which is the boundary of separation between mu1 and mu2. Alright. Let's say this is the pole of the boundary of separation, and this is the principal axis. Object O, and this is an incident ray IR. Let's say this is the normal at the point of incidence. So this becomes the angle of incidence. And the normal for a curved surface must pass through the center of curvature. And let's say this is the refracted ray. Alright. So if this is the normal at the point of incidence, this then becomes the angle of refraction R. Refracted ray, normal. Now, two refracted rays will constitute the image, right? One is this refracted ray, the other one is, imagine a ray like this. I is 0, So R would be 0, then that ray would get refracted, undeviated. That ray would go undeviated. So this is the second ray. And the two rays intersect at this point. So this must be the image I of the object. Oh, this must be the image I of the object. Oh. And let's call these angles as alpha, beta and gamma. Alpha, beta and gamma. Now, I is beta minus gamma. Realize that? This I is beta minus gamma. And this R is alpha plus beta. This R exterior angle is alpha plus beta. Now the principle that is applicable at the point A is what? Snell's law. I can apply Snell's law at the point of incidence. Mu1 into sin I must be mu2 into sin R. That's Snell's law at this point, right? But I can write as, okay, since I and R are again regarded very small. This I and R are again regarded very small. I can replace sin I by I and sin R by R, because I and R again would be regarded really small angles. So sin I can be replaced by I and sin R can be replaced by R. Alright. So then I have like a mu1 times I is mu2 times R, which means mu1 into I is beta minus gamma, I is beta minus gamma, is mu2 into R, and R is alpha plus beta. Right? Collect terms. Minus mu2 alpha minus mu1 gamma is mu2 minus mu1 beta. Beta collected on one side, alpha gamma on the other side. Minus mu2 alpha minus mu1 gamma is mu2 minus mu1, right? Now, alpha, beta, gamma are small angles. They could be replaced by their tangent, right? So then I end up getting minus mu2 tan alpha minus mu1 tan gamma is mu2 minus mu1 tan beta. Right? From A, drop a perpendicular. This is Q. PQ, like before, is really small because A and P are very close to each other. What's tan alpha equal to? Tan alpha is AQ by QI. Is AQ by? Tan alpha is AQ by QI. But be it QI or PI, it's the same, right? So tan alpha is approximately AQ by PI. So this tan alpha to be replaced by AQ by PI. Tan gamma. Tan gamma is AQ by QO, which is the same as PO. Right? Mu2 minus mu1 tan beta. Tan beta is AQ by QC, which is like AQ by PC approximately. Now, Pi is what? Magnitude of? Pi is magnitude of V, magnitude of image distance, algebraic image distance, right? Is mod V, magnitude of image distance, and PO is what? Magnitude of object distance, mod U, and PC is magnitude of radius of curvature, mod R, right? Now, for the figure, V, is it positive or negative? Negative. Why? Because it's measured in the same direction as this is the incident ray. It's measured in the same direction as the incident ray. So, for the figure, V is negative. So, mod V would be equal to minus V. Now, to locate the object, you're moving in a direction opposite to the direction of the incident ray. So, U is positive or negative? Positive. So, mod U would be equal to U. Mod U would be equal to U. Now, again for the figure, to locate the center, you're moving in a direction opposite. So, R is positive or negative? So, mod R will be equal to R. Mod R would be equal to, right? So, plugging in the same, Pi is minus V, PO is U, and PC is R in this expression. You get like a mu2. Pi is minus V, we'll cancel this by V, minus mu1, PO. PO is U, is mu2 minus mu1 by PC. PC is R. This is like an almighty relationship for refraction on spherical curved surfaces. This is mighty almighty. Mu2 by V minus mu1 by U is mu2 minus mu1 by the radius of curvature, where U, V and R are algebraic. U, V and R are algebraic. Now, again, it didn't matter whether this surface was like this or it was like this, because sine of R would accommodate both kinds of surfaces, be it a surface disposed like this or be it a surface disposed this way. The sine of R would manage everything in the same expression, same equation. Alright. Now, the important thing is, this mu1, there are two media involved here. One, mu1, the other one, mu2. This medium is called the object space. This medium is called the object space. This medium is called the image space. And very misleading to call that the object space and this the image space. Your first temptation would be to believe that, well, object space because the object is located, image space because the image is located. In fact, right now, the object space is where the incident ray lies. The object may or may not even lie in this space. The object may or may not even lie in the object space. The object may or may not lie in the object space. The image space is where the refracted ray lies. The image may or may not be located in the image space. The image may or may not be located in the image space. In fact, the object space may not have anything to do with where the object lies. The image space may not have anything to do with where the image lies. In fact, I'll demonstrate in a little while that the image may actually lie in the object space, the object may actually lie in the image space, or neither the object lies in the object space or the image space. It could lie in a third space. And same with the image. It may not lie in the object image space or the object space. It may lie in some other space. Alright, I'll demonstrate that. So, one thing. They could lie in the same space. Both object and image may lie in the object space. They may both lie in the image space simultaneously. Or both may not lie in either of the two spaces, object space or image space. That's why it's misleading to call this the object space, misleading to call this the image space, but that's the name given to it. It's only because the incident ray lies here, it's called the object space. Only because the refracted ray lies here, it's called the image space. But it has nothing to do with where the object lies, where the image lies. I'll demonstrate in some time. But even before that, the way to read this equation is image space refractive index by algebraic image distance minus object space refractive index by algebraic object distance equals difference in the two refractive indices divided by the algebraic radius of curvature. Alright. Now coming back, justifying what I said a little while ago, can I just remove this? Say, this is mu1, this is mu2. mu1, mu2. There is a ray of light. Incident. In the absence, it could have come here. There is a beam that is attempting to converge at this point. There is a beam which is traveling here and is attempting to converge to this point. But then it's intercepted by a boundary of separation between this pair of media, and in the process, this beam converges to this point. Right? Now, for this beam, for refraction on this surface, there is an object. And this is the object. It's a virtual object. And there is an image. In this case, the image is real. Because rays of light are actually converging to this point. There is an image here. Right? So, what you see here is that the object not lying in the object space. The image lying in the image space. That's one possibility. So, object not lying in the object space, image lying in the image space. You could have also had an object O. After refraction, this is what happens. These are the two incident rays. These are the two refracted rays. Realize that after refraction, they appear to be coming from I. So, what kind of an image is I? Virtual image. Does it lie in the image space? This is the image space. In this case, the object lies in the object space, the image lies in the object space, right? So the image not lying in the image space, in this case, then I have to solve. Plane mirror. A little more plane mirror, for example, right? There's an object P here. There's an object P here. And its image is P prime here. Now rays of light that are getting reflected from the mirror are incident on the surface. See, rays of light that are getting reflected from the mirror are incident on this, right? Now as far as this surface is concerned, mu1 and mu2, as far as this surface is concerned, separating mu1 and mu2, what's the object? P prime. The object is P prime, and it does not lie in mu1. It could lie in a space behind the mirror somewhere here, which may not be either mu1 or mu2, right? See, the object is not lying in mu1 or mu2. For a ray that is intersected, that intercepts the boundary of separation, that ray seems to be coming from P prime. So P prime is the object for further action on this surface. So P prime should be treated as the object for further refraction. But so this is the object. Does it lie in mu1 or mu2? No. So object does not lie in the object space. Object does not lie in the object space or the image space. Anything. And so which means, the object space and the image space have actually nothing to do with where the object is or where the image space is. Object space would be only where the incident ray lies. The incident ray lies in mu1. When refracted, the refracted ray would still lie in mu2. So this is the image space refractive index. This is the object space refractive index. Are you sure about what I said? Right? No, it could have been formed anywhere depending on the surface. I mean, we could have had, for example, a refraction of this kind, and it could have been formed here, for example. This could have been the image, right? This could have been the image. It could have been anywhere, depending on the nature of the surface, the distances involved, etc. It may have been anywhere. Yes. For refraction, it will always apply. When it moves from a rarer to a denser medium, it will bend towards the normal. Otherwise, it will bend away from the normal. That will apply everywhere. Yeah, even on a curved surface. You mean, will that rule apply if the surface was not a plane surface but a curved surface? Yes, it will. For example, if this was a curved surface, this was the normal at the point of incidence, for example. If this was the normal at the point of incidence, right? And if this was a certain incident ray, and if it passed from a rarer to a denser medium, it will bend towards the normal. That will always apply. irrespective of the nature of the surface. Rarer to a denser medium, it will bend towards the normal. From a denser to a rarer medium, it will bend away from the normal. Yes. Can I wrap this up? So I guess this much for today.